Swayam Prabha. Digital India. Educated India.
So guys, in the last lecture we discussed random walk models for polymer chains, and the main assumption that we made was the interactions along the contour, or the correlations along the contour decay with the distance along the contour, and based on that we discussed a variety of models starting from what I referred as the freely jointed chain, where the segments were moving in an uncorrelated way, and then we discussed a one-dimensional random walk that we referred as the Drunkard walk. Then we discussed the random walk on a lattice, that was like a 2D lattice to begin with, and then we generalized to the case when it can be any lattice where the number of possible paths are like Z, right? And then we said that these models do allow for the chains folding back to itself. So let's see like what happens if I do not allow for the folding back, and that we showed for the Z dimensional random walk, and we showed that we still get the same scaling law. The mean square end to end distance is going like the number of repeat units, or the mean square end to end distance going like the number of steps or segments in my random walk. Okay. And then finally we alluded to the fact that what does the constants do mean in my equation, and I associated this B by something known as the Kuhn length, and this M as the number of Kuhn segments. And then we said that if I, for example, decrease my B or increase my M, what essentially I have is a chain that is more flexible, and opposite of that is if I have the higher value of the Kuhn length and lesser value of the number of segments, this is less flexible, or I can say this one to be more stiff and this one to be less stiff, so as to speak. Okay. Now this is a idea typically applied to flexible polymers with variable stiffness, but then there is I would say a rather better model when the chains are not really flexible. So now I will talk about a class of models for semi flexible polymers which are not really so flexible, they have certain stiffness. So of course we can do by changing the B and M in our earlier models, but then there is a, I would say, slightly improved model which is referred as the worm like chain or the Kratky Porod model. So before that, let's look at like what kind of chemistries will give rise to stiff polymers, right? So far we have not really alluded to any kind of chemistry. What we said was like the many polymer chains, so like a generic or universal behavior that can be given by the model that we referred as an ideal chain, but the idea behind it was that if I look at the polymer chain backbone that consists of my carbons, then of course nearby carbons have a bond between them, 3 carbons with adjacent have an angle between them, but then there are rotations around the carbon carbon bond which give rise to some kind of a torsion like movement, and that give rise to many conformations of polymer chains. Okay. So, the chains which are stiff have certain chemistries which prevent that kind of rotations to happen with the relative ease that we were discussing in all through, and that can happen, for example, in 3 or 4 cases. The first one is when there is some kind of a delocalization of valence electrons. And let me show you like what happens in that case. So, let us say if you have a polymer chain that contains benzene rings in place of like the usual carbon backbone, and let us say we can have also possibility of having some functional groups on the benzene ring. So, let us say if this is my polymer chain, then as you can expect, we know from the chemistry of benzene that the electrons or the valence electrons here are delocalized. It is also referred as the conjugation of pi electron, and in that case it turns out that the chains are relatively more stiff. Okay. This can also happen if, for example, there is like hydrogen bonding between chain segments. And I use the example of the DNA molecule that is not quite a polymer, but it does contain certain repeating units. In that case, I will use 2 different colors to represent the 2 segments of or 2 strands of the DNA molecule. So, the black one is one strand, and then let us say the red one is another strand. So, what really happens in this case is you have some sort of hydrogen bonding between the 2 strands that give rise to what we known as the double helix structure. Okay. So, these strands are now like locked in place due to hydrogen bonding. There is one more case when this can happen, that is, for example, if you have a strongly charged polyelectrolyte, for example, the polystyrene sulfonate. In that case, what happens is if we have like a polymer chain like this, then we have many charged groups present along the chain which do have some kind of a Coulomb repulsion, and if you have like segments of chain which have like Coulomb repulsion between them, they tend to be more stressed or they tend to have higher correlation than compared to what we discussed for flexible polymer chain. Okay, so there is one other case that happens when you have a bulky side group present on the polymer chain. For example, if we have something like so now you have a large side group C6H13 present as a side group here, and because of that you do not have easy rotations around the backbone or the carbon nitrogen bond in this particular case. Okay. So, in these kind of chemistries, maybe like more chemistries, we have to think beyond the flexible chain model. We have some inherent stiffness, at least for certain distances along the contour. Okay. So, for these kind of scenarios, we will develop what is known as a worm like chain or a Kratky Porod model. So, the worm like chain or the Kratky Porod model builds on an earlier model we have described, that was the freely rotating chain model with one small change. So, the model we discussed, the freely rotating chain, was something like this. So, the two consecutive segments are at an angle theta with each other. So, the next segment will again be at certain angle theta and so on. So, now you think of like what really happens when theta becomes very small. In that case, our chain will look something like this, which is more stiff than compared to the case when theta was large. So, if I take a limit of the freely rotating chain model for the case of small theta, what do we get is a worm like chain model. So, just to recall, the correlation of bond vectors in the case of freely rotating chain was b square multiplied by cos theta to the power absolute value of n minus m, and then I want to take a limit theta going to 0, and now you can see what theta going to 0 means. The cos theta is going to 1, and unlike the case when theta was like a larger number, in that case the cos theta is much smaller than 1, and so we have a decaying correlation as n minus m increases. In this case, the correlation decay less rapidly with increase in my n minus m. So, I will discuss one other idea that we will use more frequently in the course, and the idea is that I can represent the chain of course like a line, as we have been doing in many cases, and as I was telling you, I can talk about a distance along the contour. If I simply measure the distance along the contour, this can be discussed as the contour length. So, I can discuss the chain in terms of a contour variable s, that is going from 0 to some value L c, where L c is my contour length. So, I gave the analogy with a rope. If the rope is like in a folded state, then I can move along the contour of the rope, and the distance we measure is the contour length. The other way to think about it is, if we stretch the rope, the length that we see is my contour length. So, if I stretch this, what essentially I will have is a straight line of a length L c. Okay. So, now if I look at my polymer chain in this way, so now we do not really have segments. Of course, I can represent it with segments of this sort, that is will be the case for the freely jointed chain. But what will happen if I set, for example, b going to 0? Then what we will have is, we will have something that really follows the contour of the polymer chain, and this is the idea we will build here. So, we look at b going to 0. So, in the earlier cases, if I used a representation like that for a freely jointed chain, in that case these become my bond vectors B1, B2 and so on. And if now I set that the length of this vector is going to 0, in that what you can see is the tangents will give you the bond vector. Okay. So, when B is going to 0, the bond vector is the tangent. Okay. So, the other way to say that is I can now represent my chain again like this, where I have variable s going from 0 to s equal to LC. Any position on the chain, I can say something like R is a vector s, and if I draw a tangent there, let me call that u of s, that will be the limiting value of the bond vector when B is going to 0. So, I can say u s is something like drs by ds, which is the bond vector at s for B going to 0. Okay. So, this is the idea we will use in the case of Kratky Porod model. So, now let us look at this in more detail. So, earlier I had something like this, and now since I am representing the polymer chain as something like a line going from contour variable s equal to 0 to s equal to LC. So, I can think of like the 2 points along the contour N and M, and the contour length between these 2 points become my L, and so I can write N minus M as something like L divided by B, where I will soon take a limit B going to 0. Okay. So, then if I replace this quantity by L by M in there, what we have is Bn dot Bm is equal to cos theta to the power L by B. Okay. And this has to be multiplied by B square in both the cases, just like we had earlier. So, in any case we are taking a limit B going to 0. Okay. So, now since theta is going to 0, we can think of this function cos theta in terms of its Taylor series. So, we know how we write Taylor series. So, for f x plus h, where h is small, we can replace this with an approximation f x plus h multiplied by f prime of x plus h square by 2 multiplied by f double prime of x and so on. And in this particular case, my x value is 0, my theta is my h, and so I can write cos theta as cos of 0 plus theta. Cos theta derivative is minus of sin theta, which is minus sin 0 plus theta square by 2, and minus sin theta has a derivative minus cos theta. So, it is minus cos of 0 and so on. So, this becomes 1 and this is of course 0 minus theta square by 2, and so I can write my correlation as approximately equal to b square multiplied by 1 minus theta square by 2 to the power L by b. So, keep in mind that I can only do this when theta is small. When theta is larger, that the case we discussed earlier, we cannot do a Taylor expansion. This will only work when the theta value is small. Okay. So, now we will use one other formula that works for the case when b is going to 0, and that is the limit of p going to infinity 1 minus x by p to the power p is equal to e to the power minus x. So, this is an limiting identity that we are going to use here. So, I will use p is equal to 1 by b here, because b is going to 0. So, 1 by b is going to infinity. So, then I can write my Bn dot Bm to be approximately equal to limit of 1 by b going to infinity 1 minus theta square by 2b divided by 1 by b to the power 1 by b, and then whole thing to the power of L multiplied by b square, which will be equal to exponential b square multiplied by exponential of minus L theta square by 2b. So, theta square by 2b become the x in the identity. Okay. So, now I can write the 2b by theta square to be some quantity that I will define as Lp, which I call as persistent length. Now, if I look at it, b is very small, theta is very small, but Lp happens to be finite, because I am dividing two numbers which are very small. So, this is a finite quantity which I have already hinted at in the last class, that the persistent length is like half of the Kuhn length. Okay. So, now I can write the equation we have derived in terms of the persistent length. So, if I do that, what I will have is Bn dot Bm is equal to b square exponential of minus L by Lp. Okay. And now, since I just said I can represent the bond vector by the tangent in the limit of b going to 0, what essentially it implies is I can divide this by b square here, and these becomes my tangents at those points at n and m. So, the tangents here will be given by Bn by b, Bm by b, both for the limiting cases of b going to 0. Okay. So, what this means is finally I can write this expression as u at a position s dotted with u at a position s prime, that becomes my n and m there, is given by exponential of minus s prime absolute by Lp, because recall like what exactly is L? L is the distance along the contour, and I am using the variable s to define the contour. So, s is going from 0 to LC. So, between n and m, if I find the s values, take its difference, we will get the small l. Okay. So, this is the relation that now we can use to find the end to end distance of the polymer chain, which I will draw here as RE. Okay. So, what is RE in this case? RE is equal to the position at LC minus the position at 0. These are the s values at the two ends, and now I can replace this by an integral drs by ds from s equal to 0 to LC. So, if I simply integrate the derivative, I get the difference in the positions. So, this becomes so now if I look at the RE square averaged, what I will now have is something of the sort I have again used different variables s and s prime. Just to recall from the previous discussion, we used different indices for the two terms, and the reason was to include the cross terms. In here we want to include the cross terms. So, I am using different variables s and s prime, and so by the same kind of a math that we had, except that we have replaced the summation by the integral. What we are having now is ds prime us dotted with uf s prime. Okay. So, now we can go ahead and find the mean square displacement from there. So, now this is equal to, just I am writing the same expression here, and we already have found what this is equal to. This is equal to exponential of minus s prime absolute divided by my LP, as we have derived earlier in this case. So, now I have so this integral we can do in two parts. So, for s less than s prime, this is going to be s equal to 0 to LC, s prime is equal to s to LC ds prime exponential of minus s prime minus s by LP, and then for s higher than s prime, we are going to have s going from 0 to LC, s prime going from 0 to s ds prime exponential of minus s prime by LP. And now, since both s and s prime are going from 0 to LC, both these terms are essentially same. So, we can write this as twice of S going from 0 to LC ds. I am doing the second term here. Okay. So, now we can do the integration. So, RE square is going to be, so we collect the terms containing S inside the S integral, which is exponential of minus S by LP, and the term for S prime inside the S prime integral, the exponential of S prime by LP. So, the inside integration is going to be e to the power S prime by LP divided by 1 by LP, going from 0 to S. Actually, it should be 0 to S here, the upper limit. And so, this becomes the LP will come in the front, and now we have so this we can write as 2 LP multiplied by LC minus, if I integrate this thing, we have exponential of minus S by LP divided by minus 1 by LP, going from 0 to LC, and which is going to be 2 LP LC, and then we have plus LP multiplied by exponential of minus LC by LP minus of 1. So, I can take LP common from here. So, we have 2 LP squared multiplied by LC by LP plus exponential of minus LC by LP minus 1, which is the expression for the mean square end to end distance that we have. So, now we can see there are two variables in this problem. LC is my contour length and LP is the persistence length, and using this expression in the next class we will describe how we can look at the limits of a stiff chain. We will show that in one limit it becomes a rod like chain, in other limit we recover the relations we have got for flexible chain. So, thank you.